All right, today, welcome, Cassidy. We're glad to have you back. Um, we tried a minute mystery, and it was kind of a tricky one, but we will wait until there's two of you. It's better when you can have two people bounce things off. Somebody can ask a question while the other one is thinking. Emmy will take a significant digits quiz on Tuesday. You will take it when you get back. And we caught up. We're pretty much to the end of the unit. It's actually the first three chapters in your textbook. And I'll give you a sheet that kind of tells you what to expect on there. And the one last thing is something that is usually just review, because I've done it with the freshmen, but neither of you were here for your freshman year, so I will go over and make sure I don't go too high. Okay, I can go here with it, and that's the idea of the kinetic molecular model, which I abbreviate as just KMM. It's also sometimes called the kinetic theory. And this will be used all the way through your college chemistry, physics. Very powerful. It's a very simple concept. The main idea of it, if we can say it in real simple terms, is all matter is made of tiny particles that's CLES, there's not a D there. Tiny particles, that's the molecular part of it, in constant motion. That's the kinetic part of it. And the third law of thermodynamics says that nothing can reach absolute zero, which is when there would be no motion at all. So things are always going to be in motion. She can't even see what I was. Get her seasick here by the time we're done. There. To use this, well, actually now we have models of what, down where she can see, what a solid, easier to read, and liquid and a gas look like in this model. And in solid, we think that, if I was going to do, I'm not doing a very good job here. Not at all. Sometimes you have to know when to cut your losses. down. Oh, we'll call that good enough. And then use, like that one. Use this for my, we're going to simplify this. Connections, I think I got them all. And if I get rid of my handy, oops, not those, you got to stay. This. Oh no, no, they all went to. Anyway, you get the idea. The blue should have been able to move out of there, but they have them in all directions that they're connected. These particles are connected, and we think of them in our model as the red parts holding them together, the bonds, and we'll talk about what those bonds are inside of an atom, and then inside from one atom to the next. We'll talk about them two different, and so it could represent different things, but we think of them as rubber bands, and they're sitting there in a solid, this one, and in the middle it's going to have two more in here, and this would be like a grain of salt. They're hooked up in different arrangements in these perfect cubes. Salt is, sodium chloride is in a perfect cube. If you look at a piece of salt under a magnifying glass, it's little cubes, and even if you smash it and make it into powder and you look really carefully, all the little dust is still all perfect little cubes. It always cleaves into these perfect cubes. So the one in the middle would actually have 6 rubber bands that would be attached. So it can vibrate and it can rotate back and forth and bounce up and down in there if these were rubber bands. But it's going to stay in place. So solid, the table that you're on there, if you use your eraser and you wrote your name on the table, it's not like you come back tomorrow and the eraser parts has kind of moved off. They're held in place, so it's still going to say Emmy or Cassidy on the top of the table because they hold in place even though they're moving. Now we can't see them because they're so small and they're moving so fast. We can't see them moving, but we can do experiments and we can tell, yes, they are moving. So solid is held in a lot of places, but there's always motion, just vibration and rotation, but in the same place. In liquids, we have still attached, but just kind of in chains and beads, and they can be long chains. And there can be interaction, we'll talk about that later, in between these, even though they're in separate chains, and whether it flows in like water, it just flows right past. It's very easy. In syrup, there's interaction between these, so it kind of sticks as it goes. It doesn't pour near as fast. You wouldn't want to jump off a diving board into a pool full of syrup, because it wouldn't just get out of the way for you. It's held together more. It would be, besides the icky, sticky part of it, it wouldn't, even a beautiful dive would probably hurt a little bit just because it's not going to get out of the way for you like a liquid will. And in a gas, no connections. They're perfectly free and they're just floating around in a straight line like everything else, until it hits something, and then it'll change direction, it'll bounce off. But they're not going anywhere in particular, they're not going around anything, they just go in a straight line until they hit something. So these are the models that we're going to use to explain it, and there are 3 questions that we ask to use the model. energy added or lost? What happens to the particles? And 3, what change occurs? I probably should move this to another table. This might not be the best way to do this. Okay, we've changed locations a little bit here to show how this works. And I've got two objects, a brass ball and a brass ring. The ring is really just my measuring device. And you can see that the brass ball, not a lot of it wiggles a little bit, but it goes through. This is just a brass sphere. If I heat it up, in here, now if I was going to answer this, first question is energy added or lost? If you heat something up, you're adding energy. If you cool it, you're taking energy away from it. So I am adding energy to this material, to the particles in the brass. So if this brass is made out of tiny particles that are in constant motion, what do you think is going to happen to them as far as their motion if I add energy to them? But not because I'm adding energy. I actually don't think the particles they don't change size at all. What's going to happen to the particle if you're running and you think you're running as fast as you can, but suddenly a mean dog is chasing you and you get a shot of adrenaline, so you get some more energy, what's going to happen to your running? You're going to go faster. Same thing, if they're moving and I add more energy, they're going to speed up. And if they're moving faster and they're connected by rubber bands, as they are there, they move faster, they're going to jostle more, they're going to spread further apart. So the particles will speed up and spread out, and that's what happens anytime you add energy. No matter what you're talking about, if you add energy, the particles are going to speed up and spread out. And then what change occurs? What is going to happen to the object if all the particles spread out? It's going to get bigger. Okay, so we don't think the particles get any bigger, but if all the particles in it spread further apart, then the whole thing should get bigger, and it now won't fit through the ring anymore. It'll actually even bend the bar here as I go through. And we can do the opposite if I cool it, so that would be taking energy away. So the energy would be lost by the solid. Put it in water. The particles are going to slow down. The rubber band's going to pull them closer together again. And if all of them get closer together, then the object should contract. The way we usually talk, we say shrink. It's really contract is the word, and now it easily fits through again. So the model kind of is tested in that way that we know that it's probably accurate because all the tests seem to work. I'm going to do this from here and see if we can't keep going with this. Now, if we do other examples, let's say we're going to the whole board now right big so we can see from there. If we're going to explain melting, I've got a piece of ice and I'm going to melt it. I'm going to answer those three questions with it. So the first one, when we melt something, I mean, are we going to add energy or take energy away from it? Because we make it colder. So you put things in the freezer to melt it? No. That's the same thing that most students do with, you think, oh, melting is something's frozen, it's cold, so we think that we're losing it. But we're actually, what do you have to do to make it melt? You put it on the counter, you put it in the microwave, you put it in the oven, whatever. We're going to add some energy. We have to heat it up. So energy is added, and we always put a prepositional phrase in there because it's important to know what it's being added to. So in this case, melting is from a solid to a liquid, so it's added to the solid. And what always happens to the particles when we add energy?
Or it moves faster.
Moves faster. They don't change size. The particles speed up and spread out. And they do. If you have a flask of water and you have it marked that it's right to that point, and then you put a flame underneath and you heat it up, if you have it marked at that point that it's right here, as you heat it up, pretty soon you're going to notice that the water has risen in there and it's up there. It actually does spread out. It takes up more room. So if you heat up water in a pot right to the brim, pretty soon it's going to be running over. Even before it boils, it's going to run over and it's going to start to make a mess. Now, if we're starting from, and when we do a phase change, we always think of the models. And so we have a model of the solid, and I'm just going to do the simple two-dimensional model. My rubber bands in here of a solid, and I'm going to a liquid. You have to think, what is going to have to happen to do this? If I gave you something that looked like this, and it had a bunch of styrofoam balls and connected by rubber bands, but I said I want them to look like this. I don't want them all together like this. What would you have to do? If I had them right there in front of you, went to Hobby Lobby, put these together with rubber bands, and I said, make this look like this, what would you have to do to it? You have to what? Well, no, this is what I give you. And let me, whoops. That'll work. Perfect. Instead of looking like this, there's still 9 in this case, 9 of the styrofoam balls, and I want it to look like this. How do you turn this into this? Remove it. You're going to have to get rid of some of these. And wouldn't that, if I add enough energy and they're spreading out, what happens to a rubber band when you stretch it and stretch it? It eventually breaks. So what our model says is eventually as it breaks, this is gone, and we end up with that. And that's how we turn a solid into a liquid, is the rubber bands start breaking apart and we end up with a liquid. So we use the models to tell us what's going to happen. The solid breaks apart to form a liquid. We want to go through and say exactly why. We can't just say solid turns into a liquid. We're trying to explain why. It makes more sense. I can see it with the models if you're saying that, oh, these bonds break, and then I've got it. And it doesn't have to be just those like that. As it starts to break here and there, you might actually have one that's breaking in a way that you have a long chain more than just into nice even parts. They start to break apart, and eventually you're going to have a chain that it turns into. But visually, it's easy to picture if we can say, oh, it's just going to break apart like that. I don't know if I can take, nope, they all went together. Right. Okay, so it makes sense how to do that. Let's do one the other direction. How about you, Cassidy? Do you have any questions? No? All right, we'll move on then. Let's do condensation. Condensation is when we have a gas that changes to a liquid. So there's moisture in the air on a hot summer day. We call it humidity, and it touches a cold can of pop that you have out at your picnic or whatever, and the moisture in the air hits the cold can, and it turns into a liquid, and we get that. We say the can is sweating. We get that condensation on the outside. A lot of kids think that it's leaking. It comes from the inside, but it's actually moisture that was in the air hits the can. It's on there. That's what dew on the grass is. Moisture in the air hits the cold blade of grass, and it turns into a liquid. You take a hot shower, and moisture in the air touches the cold mirror, and it turns into a liquid. Your mirror is all kind of fogged over with that. That's just condensation. So we're going to go from this to that. That's our model that we're going to go gas to liquid, and that from those to that. So number one, the key is that, that's probably hard to read from that far away. Red, is energy added or lost? You can always tell, is this going from here to here? Is it gaining freedom or losing freedom, each particle? Is it more free here, or where is it more free? Is it gas or gas? So it's losing freedom. It's being joined together, chained up, whatever. So if it loses freedom, we also lost energy. It also happens when it touches something cold, so if you're cooling it off, it's going to lose energy. So energy is lost by the gas. I'm going to say what it is that's losing it. And what's going to happen to the particles if they lose energy? And if they slow down, what are the rubber bands going to do to them? Well, in this case, there's no slow down. But if they slow down, they're going to it's the opposite. If we heat it up, they speed up and spread out. So if we cool it down, they're going to slow down and come together. Right now. So the particles slow down, whoops, and get closer, come together, however you want to say it. said, come together. And then, same thing with this. This time, I give you 3 of the styrofoam balls, and I say, for some reason, something to do with Christmas, we want, I don't know what's going to make, maybe they're gold and we want them to look like sleigh bells or something. I want them to look like this. I give you this, and I want them to look at this. What would you have to do? Nope, forget, no chemistry here. Now we're in Hobby Lobby again. I gave you 3 white styrofoam balls. And I said, I want them to look like this. Take this, do that crafty thing, whatever. You're not in chemistry class now, you're in Hobby Lobby, and make them look like this. What would you have to do?
Maybe get like some toothpicks and like put them together.
There you go. Whatever it is, whether it's rubber bands, could be toothpicks, it could be whatever it is, string them together like that. So that's how you answer them. What change occurs? How does this happen to this? If this happens, then the gas particles and however you want to say it, join together, connect. You just can't say they come together because we've already said come together here. So some actual verb that shows that there is something that is joining them. Connect. Don't need the paint yet? Okay. Connect to, form a liquid. So energy is lost by the gas, you know that because it has to get colder. Particles slow down, get closer together, they come together, and then, and I look at the models, they're all separate here, I want them joined, so the gas particles connect to form a liquid. That's what our model predicts, and it seems to hold up in everything we've done. Make sense? All right. We will do some more of that on Monday. I will give you a sheet that tells you what will be on the test, probably the end of next week. And you can tell me what it is that you'd like more of practice, and we can go over whatever it is and talk about, discuss, or whatever. But quiz on Tuesday for you. Quiz when you get back, Cassidy. Test probably Friday, and we can work around that, Cassidy, for you whenever you get back as well. So that's it for chemistry.